Okay, so this is the next topic, which is about cut and paste. Hopefully, we all know what cut and paste is, which at this point, I hope you know what cut and paste is. So, the basic idea is that we are going to have a bunch of ingredient covering arrays, and we're going to be playing chef today. We're going to take a bunch of these ingredients. So take a bunch of CAs and combine them together in some recipe, and what's going to output is another covering array. So, and what we want to have here is just a bunch of ingredient arrays that have certain properties, like it has a certain strength or a certain number of symbols or something. And all that we're going to do is we're just going to combine them and cut and paste copies of these arrays together in some way to guarantee that the resulting array is a covering array. So the thing is with this particular subject that it can be generalized to the moon and beyond, and like literally to the moon and beyond in some cases. So what this is going to be is just a very, very simple overview of some of the main techniques that are used, and not going really deep into what can be actually done, because there are many, many directions you can go. There's so much generalization you can do that it's not worth covering, because it's generally just not interesting on its own, because it's just the same techniques as these, but in a more general context. So let's get right into it. So what we're going to first talk about is something called direct product. So what is the main idea here? So here we have two covering arrays, and they can have an arbitrary number of rows, columns, and symbols each. So there's no restriction on those, but the only thing that we're restricting to is strength 2. And this method by itself only works for strength 2. Um, Although you could try it with higher strength, but you'll need additional rows beyond what we're going to do here. But for strength 2, um, you can only work for strength 2 without additional rows. So how do you actually do this? So what we're going to do here is, let's just say here is a covering array A, and then maybe we have a skinnier one, B, right here. And what we're going to do is this. What we're going to do is we're going to take any column we want of A and any column of B that we want. And we're going to do this for all pairs of columns anyway. So let's just pick any column of A, any column of B. Then what we're going to do is we're going to take these two columns, and we're going to form an array C that's really, really wide. So a very wide array. So C here. And what's going to happen is that we're going to take the column that we took from A, and we're going to put it on top. And then we're going to take the column from B, and then the one we selected from B, and then just put it right underneath it. Okay, so we're going to take any column we want out of A, any column we want out of B, put the one from A on top and the one from B on the bottom. It actually doesn't matter which one you put on top, but you put as long as you put all of the columns from one on top first, then it doesn't matter which one you put on top. And what we're going to do is we're going to do this for every pair of columns. So this is going to be done for every column of A, every col of B. So if A, for example, has 30 columns and B has, let's just say 15 columns, then C is going to have 30 times 15 columns, because it's every pair of columns, and that's going to give us 450 columns. And the number of rows we get is going to be the number of rows in A plus the number of rows in B. Because we're just stacking one on top of the other. That's all we're doing. And why can we guarantee that this is a covering array? Well, let's see. If we have if we pick two columns in the resulting array, well, that is the result of picking a column I out of A, so this is from A, as well as column R right here. And from B, we have column J and column S. So the second coordinate is from B, the first one's from A. So let's see. Why can we guarantee that these are covered? Well, let's see. So then if I is not equal to R, well, that tells us that those are two different columns of A. Well, because A is a covering array with strength 2, then all interactions are covered in A by definition. And then if J is not equal to S, well, that is the result of picking two distinct columns out of B. Well, we know it is a strength 2 covering array, so we get exactly the same thing, but for B. And then, well, could there be any other pair? Well, if neither one of these two is true, then that means that I is equal to R and J is equal to S. So that means we pick the same column out of A and the same column out of B. Well, that's not possible because we're just looking at all pairs and we never pick a pair twice. So there are no interactions of this form. So that means that every single interaction either has the first coordinate different or the second coordinate different or both. So therefore, the resulting array really is a covering array of strength 2. And the really nice thing is that we have a very modest number of rows growth, but a gigantic number of columns growth. And let's say that one thing that you can notice here is that what if we use the same covering array to start with? So let's just say that A and B are exactly the same covering array. Then what we will get is, so if A is a covering array of n rows 2kb, then let's see, so what can we get? Well, and then B is the same. So then A times B, so I'll call this operation times. So A times B gives us a covering array with 2n rows, strength 2, and k squared columns and v symbols. Well, now suppose we do that again. So let's just say that we let C be that array, and let's do C times C. Well, then we get a covering array with 2n plus 2n rows, which is 4n. And then, let's see, then we get strength 2, but now we get k to the 4th columns because k squared times k squared. And in general, what we get is something like a covering array of 2 to the I n rows, strength 2, and k to the 2 to the I columns with v symbols. So what we can notice here is this automatically tells us that the growth rate is at most log n, because compared to the number of columns, the number of rows is some constant times log n, times the logarithm of k. And for that reason, we get a logarithmic upper bound for strength 2 automatically out of this method, which is another proof of it. So we could use probabilistic method, or we can just apply this method, which is actually constructive too. So it tells us, well, just pick any old starter array that you want, any old covering array to start with, and you can just apply this operation over and over and over, and you'll get a covering array of a logarithmic size, which is pretty nice. And it works for any number of columns, any number of symbols. Whereas the the optimality that we know for strength 2 is only when we have 2 symbols. But this works for any number of symbols. It gives us the right asymptotic growth, but it doesn't give us necessarily the optimal size. And it turns out that this is not true, that we get the optimal size every time, because there's a lot of duplicate coverage. And I'll invite you to figure out why that's the case and actually try this yourself to see where the duplicate coverage actually is. But one thing that you may try, and to try to reduce the coverage, is what if we have in the covering array A, we have a bunch of zeros for the first row because we can always standardize a covering array. Then we do exactly the same thing for B. Then what we'll get in C is 2 whole rows of zeros. Well, if we have a duplicate row now, we will have complete duplicate coverage. So we can actually strike out one of the rows of zeros. So if we standardize the 2 arrays, we could we have a duplicate row, and we can decrease the number of rows by 1 each time we do the product, which is kind of cool. So we could actually reduce the number of rows here quite a bit, but it turns out you can do a lot better if you have a lot of constant rows in the covering array. We can't guarantee in general that we could ever get more than 1. And in fact, there are some arrays where you can only get exactly 1. So if you have arrays with more constant rows, then you could generalize this much further and actually remove even more rows. And there are actually other generalizations where you have not the same number of symbols every single column. So here we have V symbols every column, but if you have a different number, then you can actually generalize this even further. But I was going to put this in, but it's just a mess of an actual statement here, and it's just not worth our time here. But just note that if you're interested, there are many ways we can actually generalize this to reduce coverage for strength 2. So remember, this is only for t equals 2. Because if you tried t equals 3 here, then what could happen is, what could happen? Well, we got to pick 3 sets of columns here. Well, it could be that 2 of the columns are the same and 2 of them are different. Sorry, the other one's different. So here, we don't necessarily, we can't guarantee that for t equals 3 or higher, but for t equals 2, because we can only pick 2 columns, it can't be the same that I is equal to R and J is equal to S. But if we pick 3, it could be that we will always have 2 that are the same and 1 that is different, and you can't necessarily guarantee every triplet is covered. And even then, you would have to start with a strength 3 array to start with anyway. So, which isn't really a problem, but it's just something to keep in mind. Okay, so here's another technique that you may try. So what we have here is something called compatibility. So let's just have 2 arrays right here, B and B prime. And we say that these 2 arrays are compatible with parameters L and R, such that no matter what symbol that you pick up to R, so in this case, V has to be at least R for this to even work. Then let's see. So what does this actually tell us here? yeah, so the J here is any column that you want. So let's just say we pick column J in the first array. So let's just say this one. And then J prime in another one. So any column over here. Then there's a row. So this row is the literal row in the covering array. So let's just say this one. And it has to be the same row in both. The column J and J prime could be different, but the row has to be the same. And there's an upper limit called L. So maybe I have this as the limit. So let's just say that this is the Lth row. Then we have to guarantee this for the first L rows. It could be, this might not hold for rows later on, but up to L rows it has to hold true for every choice. So then this says that there is some row in here. So let's just say the one that I have in red here, it doesn't have to be the same for every choice of symbol, but it just has to be some row within the first L rows. Then there must be some row, the red line here, where the entry at these intersections is the same. So in a sense, what these covering arrays are is just that they're compatible in terms of where symbols actually appear. And if you can actually guarantee that, then again, this is a huge generalization of what you can do, because LR compatible is basically a generalization of the standardization idea. Because if I just say that I set L to be 1, so if I set L equal to 1, and I standardize the two arrays, well, that says that in every pair of columns, and let's see, so then R would have to be 1 here in this case. So what does it say? Well, in that first row, for one particular value, the two rows are exactly the same because there's only one row to choose, and it has to be true for every pair of columns. Well, if it's zeros across the board for the first row, then they're in complete agreement. So this actually tells us that every pair of covering arrays that are standardized, so remember they have to be standardized, are 1-1 compatible. But being able to generalize this to more rows or more symbols will actually allow you to eliminate even more coverage. You can actually reduce rows this way. So again, it's another generalization I'm just not going to go into. But if you're interested, I can give you some resources for that. Okay, so this is actually kind of like a cut and paste idea, where we're just literally cutting and pasting columns into the resulting array. But let's actually start cutting and pasting whole arrays versus just a single column or something. So this technique we're going to see here is a technique of Roux a long time ago in his PhD thesis, believe it or not. So it's actually pretty simple. So the idea is, let's just have a covering array of strength 3. So this is A right here. And what I'm going to do is I'm going to literally just horizontally juxtapose another copy of A. No changes whatsoever. And what I'm going to do down here is I'm going to have an array called B. And under the other copy of A, I'm going to have an array called B complement. So what are these? Well, this is an array with t equal 2. And this one is same as B, but we exchange the 0 and the 1. So like if it was a 0 before, it becomes a 1 now. If it was a 1 before, it becomes a 0 now. And what this is, let's do purple. So this whole thing is a covering array with 2k columns, so twice as many columns, with t equal 3. And why is that the case? Well, if I pick 3 columns out of one side here, well, A was a covering array of strength 3, which means that this interaction here was covered because A is a covering array of strength 3. Same thing if I pick 3 columns over here. Because A was a covering array of strength 3, I just literally copied and pasted the whole array. Now, what if I pick 2 columns on this side and 1 on the other? Well, if these 3 columns correspond to different columns of A, so it's not like we pick the first column here, the 5th one here, and then this one has to be the 9th column or something. So these 3 correspond to different columns of A. Well, the coverage of A still holds because I just literally copied and pasted the whole array. So the only issue comes when we pick, let's say, the first column here, the 5th column here, and a duplicate column on the other side. And it's symmetric if I pick the 2 on the right side and 1 on the other one. So it's not possible for me to pick 3 columns which are the same because I only have 2 copies. So let's assume that we have something like this. Then what you can actually show is that, so what can we do here? Well, what can we do? Well, in these arrays, every covering array of strength 3 is also one of strength 2. So just to give an example, so this has to be with 2 symbols in order for this to work with the B arrays down here. So so what we know is that the array over here covers 0, 0, 0, 1, 1, 0, 1, 1. And so the array A has to see these 4 because every covering array of strength 3 is already one of strength 2. So that means on the right side, the 5th column also has 0, 1, 0, 1 in the same places. So let's keep track of the 8 interactions we have to see. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Well, in the top half with the A array, I have the 3 zeros. I have 0, 1, 1 checked. I have 1, 0, 0 checked. And I have 1, 1, 1 checked. So the other 4 I don't have yet. But now let's go down to the B arrays. Well, B is a covering array of strength 2, which means it has 0, 0, 0, 1, 1, 0, 1, 1. But the B complement array must have a different position in that second column, the 5th column here. So that means on the other side we have 1, 0, 1, 0, which is the opposite of what the 5th column was on the other side. So that means we get the other 4 entries here as a result because the 3rd bit was flipped. So this actually shows us that we can get a covering array with n plus m rows, where n comes from the covering array of strength 3, m is the one from strength 2, and we get twice as many columns as a result. So this is not as good as the construction we did with for t equal 2 that we did before. We only get 2k columns out of this, but it's still pretty modest in that we only have a small number of rows added, because what we showed before is that for covering arrays of strength 2 with 2 symbols, can of 2k2 is approximately log k. And we know that these are optimal. But the covering arrays of strength 3, those are log k2, but they have a much larger constant compared to the strength 2 one. So the number of rows that we're adding with the B arrays is quite a bit smaller than the ones with the A array. So it's only a very modest number of rows that we're adding here, which is kind of nice. But you can actually generalize this further. And here's the basic idea. So we're going to start exactly the same way. So we have A up here with a copy of A. And what I'm going to have here is a bunch of copies of B. So again, B is the covering array of strength 2, but now we have V symbols instead of 2. V could be equal to 2, but we're just generalizing it to V symbols. So we have a bunch of copies of B. Then what we're going to do is we're going to, in this part right here, we're going to have something that I call pi B. And what is this is we're going to, in this case, we're going to send 0 to 1, 1 to 2, 2 to 3, and then etc. up to v minus 1 is sent back to 0. So we're cyclically changing the symbols here. So that's essentially what we were doing, but in a different way. We were changing zeros and ones, but if you think about it, if we send 0 to 1 and then 1 to 0, we're just adding 1 modulo 2 for the 0 and 1. Well, here what we can do is add 1 modulo v. So it's exactly the same idea. And then here for this one, we will add 2 modulo v. This one will add 3 modulo v. This one will add 4 modulo v, etc. And then in the last one, we will add, let's see, what would it be? So it would be v, we will add v minus 1 modulo v, which is effectively saying we're subtracting 1 mod v in that particular case. So we're just cyclically changing the symbols, and by the argument that we did before, you could actually show that this is a covering array of strength 3 with v symbols instead of just 2 symbols. So it's a generalization of Rue's work. And the number of rows we get is n for the initial strength 3 array, and then v minus 1 copies of the strength 2 covering array. And we still get the same number of columns, but we can have many more symbols as a result. And this idea can actually be extended further, but the problem mainly there is, well, for strength 4, what could happen is, let's just say we have, let's just say that we have, so these are of strength 4. Well, it could be that we have 2 columns here and 2 columns on the other side. Whereas with strength 3, you can't have a column in 3 distinct parts because there are only 2 parts. But when you get to strength 4, that's not possible anymore. Oh, actually it is possible now. You could have 2 columns on either side. And there are some generalizations that I've tried to look into, like what if we had strength 3 and we had 3 copies of A versus just 2? What would you actually need there? What if we had a bunch of copies of A instead of just 2 or 3 or something? What would you actually need? And this is actually the subject of ongoing research, and the answer is not actually quite known here. Even for strength 4, I don't think it may be written down, but I'm not exactly sure what you can do there. But I know it's been generalized in some way based off of Rue's construction here. But the basic idea is that we're just copying and pasting multiple copies of the same array and maybe modifying it, like in the case of these arrays right here. So that's all I have to say on cut and paste. So on Friday, we will be talking about these and the combinatorial techniques we covered on Monday in the paper by Colborn on Friday. So I'll see you then.